Welcome to the lecture. We will discuss a bit more about differential forms. So, these differential forms help us to set up an alternative to vector calculus, which is known as Cartan extradial calculus. We will discuss the key ingredients of it. So, this is the main thing that we will going to discuss. First, we will recap about differential forms. Then we will introduce three operation. One is wedge product, which is denoted by this capital lambda, exterior derivative operation denoted by this small d, and Hodge star operation denoted by this star. Now, in the previous lecture, we have introduced the differential P forms as a completely antisymmetric 0, P rank tensors, and they form a subspace, or rather a vector subspace in the tensor space of 0, P rank tensors, and we denote that subspace by these capital omega superscript p, and in d+1 dimensional spacetime, the dimension of this omega is this, given by this binomial coefficient, that is d+1 to p. Now, let's consider this direct sum space. So let's consider all the forms from 0 form up to the p form in p dimensional space. It can be a completely Euclidean space Rp, or it can be like Rd, 1 with p equal to d plus. For example, 3+1 dimensional Minkowski space. So if we consider this Dirac sum space, it turned into an algebra under this wedge product. Remember when we can call a vector space algebra? So if we introduce a new binary operation which takes two elements of the vector space and gives back another element in the vector space, then under that operation, binary operation, the vector space is closed and turned into an algebra. In this case, that operation is nothing but this wedge product. So for example, let's take one form, omega and these xi, and let's take the wedge product. So each of them we have written in terms of a component and basis, and for this also. So then we have this, and this is the basis element of this wedge product of these one form, which is dx mu wedge dx mu is nothing but this is the completely antisymmetric product of these two coordinate differential. And then we can rewrite this thing into two parts. One is symmetric and one is antisymmetric. Remember, these dx mu wedge dx mu is completely antisymmetric. Now, when these mu indices are contracted, and then it is very easy to argue that because this is symmetric, this is contracted with the symmetric thing, this is will not contribute, only this will be there. Okay. Now, this is nothing but a two form. Right? So, wedge product of one form to one form is a two form which we denoted by this capital D, whose component are now these. You can see this is antisymmetric in mu nu, and dx mu wedge dx mu provides the corresponding basis. So you can repeat the same exercise by taking a one form and doing a wedge product with respect to a two form. You will see it gives a three form, which means the object will have three indices or its component, which will be completely antisymmetric in these three indices. And of course, in the previous lecture, we have written down the basis elements for this three form, which come from wedge product of taking three coordinate differentials. Now you can easily see that this direct sum space omega is closed under this wedge product, and hence forms an algebra. So before we proceed, note that you can take the 4 volume element of Minkowski space-time denoted by d4x, and you can easily show that this is nothing but the wedge product of this dx naught with dx dy dz. So this is the time component. These three are the comes from the spatial part. You take the wedge product of this coordinate differential. This gives you the d4, the elementary volume. Now we move on to the discussion of something called exterior derivative, which we denote by this small d. Now it takes a p form, gives you a p plus 1. So let's take a generic p form, which we denote by omega p. So we can write it as usual. It's a 1 over p factorial. Then this component which have p indices, and it's completely antisymmetric in this indices, and this forms the basis for these p forms. Now d of omega p is given as 1 over p factorial, then del of mu acting on omega, and then we have this p plus 1 coordinate differential and the wedge product. You can see they form a basis of p plus 1 form. Now you can do antisymmetric swap between mu and each of these mu indices. So we will have total p plus 1 term, and from this you can rewrite this in this following way. Remember that this is completely antisymmetric, and each of these terms is contracted with this antisymmetric part. So if you keep that in mind, you can actually rewrite by interchanging the corresponding indices, one of the mu indices here and with the new indices, and because they are summed over the dummy indices, you can re-level them. So this p plus 1 term will actually add with each other and gives p plus 1 times this term, and this is divided by 1 plus p plus 1 factorial. So this p plus 1 factor from the numerator will cancel it and you will get that. So do this exercise explicitly just to get familiar with this kind of manipulation. So let's take an example of this exterior derivative. So we have discussed that we can write down this Maxwell bound-form potential by this way, where we can identify the zeroth component up to some sign with the electric potential, and the other three components come from the magnetic vector potential that we have discussed in the previous lecture. So now d of a is basically del mu of this and then wedge product of dx nu. And now you can just use this antisymmetry of this to rewrite this term in the following way. So remember that mu nu is contracted with this, and this is antisymmetry. So if you swap and relabel them, so these two terms will be same, and this will give back this first term. Now, if you look at it carefully, this is nothing but the Maxwell field strength that we are familiar from electrodynamics. So we write this as F nu mu, and so dA gives the F, the Maxwell field strength, which is a 2 form. In fact, you can show that the two homogeneous Maxwell equation, which does not involve any source, that is del dot b equal to 0 and curl of b is equal to minus del b del t, those set of Maxwell's equations comes from these equations. We'll discuss it a little bit more later on, and you can recast those Maxwell equations neatly in terms of this equation, df equal. Please try to do so by yourself, but we will come back to this equation again when we try to covariantize the Maxwell's equation in the subsequent lectures. Also try to see what happens if you take a zero form, which is just a scalar, and take a d of it. You should be able to see what happens. Now, one important property of this exterior derivative is that if you apply twice, d square, it gives it. Remember, this is an operator. This should act something. So d square acting on, let's say, p form will give you 0. Why? Remember, each of the d gives you a partial derivative, right? So 2d will give you 2 partial derivatives. Now you can exchange 2 partial derivatives. They are symmetric, but remember they are contracted with the antisymmetric combination or basis. Hence, you can easily show that d square of omega p is 0 due to the fact that, as I just mentioned, the symmetry of the exchange of 2 partial derivatives. Okay. Now, just like ordinary derivative, this also follows Leibniz identity, and we leave that for you to show. So you take two form, a P form and Q form, and take a wedge product, and D acting on them will be distributed on them. But you have to be careful about this sign here. Also note that, so if D of a form vanishes, then we call that form as a closed form. And if you take a P form, and if you can write it in terms of D of a P minus 1 form, then we call it as exact. Naturally, all exact forms are closed forms, because D of A will be D square B, and that is it. Example is, again, as just we discussed, is the Maxwell field. So F equal to dA, and then you can see that D of A should vanish because D square A is 0, and that gives you the homogeneous Maxwell's equation, that is Maxwell's equations without involving any source term, which corresponds to the del dot B equal to 0 and curl of E equal to minus del B del. Now we go on to the next operation, which is the Hodge-Star. So note that the dimension of this omega p, that is space of these p forms in D space-time dimension, is nothing but this. Also note that if you have D minus p forms, and the dimension of that corresponding vector space is nothing but this, given by this binomial coefficient, and we know that these two are same. So now, if two finite dimensional vector space have same dimension, they are isomorphic. So we can map element of here to an element here, and this Hodge-Star precisely. So if you take the basis of this omega p, which is here, and then we can define the star operation by this way. So this is the basis of p forms, gives the basis of D minus p form, which is multiplied with this Levi beta, where first p index is up and the last D minus p indices are down with this factor. So remember that Levi beta we have defined is a completely antisymmetric tensor. This is a generalization of that. So you can lower these indices by multiplying the inverse of this Minkowski matrix, and you can have the conventional Levi beta. Also, it has capital D number of indices, because remember that for a D space-time dimension, you cannot have more than D form, right? So more than that will automatically vanish by antisymmetry. So regardless of this hybrid nature, you can show that this is completely antisymmetric. So one important thing that one can show, that if you take 2 star of a form, and it will give us a form, but with some minus sign raised to the power this factor. So depending on p and space-time dimension, get a -1 or plus. Now, given this wedge product and the Hodge-Star, you can define a inner product of two p forms. So you take two p forms, alpha and beta p, and the inner product is defined by P. Take alpha P, weight star of beta P, and integrate over all space denoted by this integration. This is the P form. Star of P gives you a D minus P form. That is what we just discussed. And the wedge product of a P form and a D minus P form gives you a D. Remember that this is actually gives you a ready-made volume integration. How that is the case? Let's quickly discuss that. So alpha P wedge star BP. So there will be some number or in general a function coming from the component of these two, which we write here. Remember that eventually it's a D form, so it will have basis which will have dx mu1 wedge dx mu2 up to dx mu d, and this is nothing but the volume element. So you can see that you can write this volume integral neatly using this form language, and you can define this for any P form, and it satisfies all the properties of the inner product in a real vector space. That is, it is symmetric under interchange of alpha beta and positivity condition that you take to inner product of alphas, which is to be greater than equal to 0, and this equality hold only when alpha P is itself 0. Now, as you can define it for all the P form, then you can conclude that the omega, which is the direct sum space of the P, all the P forms from 0, 1, 2 up to P, is now an inner product space. So one small exercise that we leave it for you to do is that we show this. Now one more ingredient we can define with the help of this star and the D operation is something called a adjoint of extrude derivative, denoted by this small symbol delta, also known as co-differential. So you take a P minus 1 form, and the co-differential of the P form alpha is defined as inner product of D of this P minus 1 form beta and alpha. Essentially what it does, remember the extrude derivative, it increases the rank of the form. It gives a P plus 1 form from a P form. Now this co-differential does the opposite. It lowers the rank of the form to give a P minus 1 form. In fact, try to show that the co-differential of P form is this. And you can check what is happening. So the dimension. So you have omega P, which is the P form. So star of omega P gives you D minus P form. So D of star will increase it by plus 1. Then take star, which gives you D minus P. So you can see it gives a P minus 1 form. So try to show this relation. Now we have all the ingredients that we need to set up the extreal calculus. And now it is possible to reformulate, for example, the vector calculus in R3 in terms of this thing. We leave it as an exercise for you to do. We'll discuss it in the next tutorial video. Thank you for listening.